Welcome back. In the previous class, I have talked about the input output stability of linear time invariant systems. In today's lecture, I am going to extend same kind of concept for the discrete time system and time varying system, and obviously I have told you that my discussion is limited on the linear system. So the main goal of today's lecture to introduce the input output stability notion for discrete time system and time varying linear system. It means that we are again going to see that how the magnitude of output relates to the magnitude of the input in the absence of initial condition, same like previous lecture. So again we are just going to talk about the external stability of the system, and one of the main assumption again is that our system, either discrete time system or linear time varying system, is in relaxed state. It means that all state variable, all internal variable are equal to 0. So let us start the lecture. So somehow this lecture is just the straightforward extension of the previous one. So whatever concept I am going we have seen for the continuous time LTI system, same kind of concept we are going to extend for discrete time system. But what is main difference whenever we are talking about the continuous time system? In continuous time system, input variable or output variable are available for each and every time moment. But whenever we are talking about discrete time system, at that time we are talking about the sequence of input. It means that I am assuming that I know the input at some instant k equal to some kind of integer 1, 2, 3, might be 0 also, but we are not worrying that what kind of things is going to happen between instant k equal to 1 and k equal to 2. So I have some kind of discrete information about the input and output. And again, whenever we are talking about input and output stability, at that time we have to apply some kind of bounded input to the system. So now I have to talk the concept of the bounded sequence, because we are applying bounded sequence and we are hoping to generate some kind of bounded sequence. So first I have to take help of mathematics to recall the notion of the bounded sequence. So an input sequence uk is said to be bounded if uk does not grow to positive or negative infinity, or in another way one can tell that there exists a constant, and that constant we are telling that nothing but some kind of constant I have, and that constant is such that for each instant k 0, 1, 2 up to infinity or up to n, you can tell that this particular relation is going to satisfy. Now let us come to the definition of the bounded input bounded output stability of discrete time linear system. So a system is said to be bounded input bounded output stable if every bounded input sequence excites a bounded output sequence. So since I have only information about the discrete instant, so we are assuming that each discrete instant is going to provide some kind of output in relaxed state. Means initially we are assuming that system is in rest, and whatever output that is we are going to obtain, that also should be bounded. And again in order to picture this, I am going to state the theorem same like the linear time invariant case. So a discrete time single input single output system. So first we will see what kind of result is going to come for single input single output system. And because beauty of single input single output system that it is pretty easy to tackle. Due to that reason, first we are stated result for single input single output system, and after that we are extending that result for multi input multi output system. So again I am assuming that discrete time system is linear, time invariant and causal, and I hope that now you are familiar with the definition of each and every terminology. And if I know the impulse response sequence of the discrete time system, then using some kind of convolution operator, I can able to define the output. We have already seen this kind of formulation, and in our means what we are telling that if k is only available on discrete instant, then integral in case of continuous case, that is actually replaced by some kind of summation. And here I am assuming that system is on rest. So basically whatever output we are getting, that is just due to the control input. So there is no need to worry about the state of the system. Now let us see that how basically what is a statement of this theorem. So I hope that you are aware about this expression yk, and this is gk minus m. Gk is the input response sequence. Here now you can see that if I have linear continuous time LTI system, and if that is single input single output, at that time we are defining g as a impulse response function. If multi input multi output system, then impulse response matrix. If I have discrete time system, then we are defining that as a impulse response sequence, because information is only available at k equal to 0 instant, 1 instant and 2 instant. And how basically one can calculate the impulse response? So output sequence excited by the impulse sequence applied at k equal to 0. So in that way I am able to generate this term gk minus m, or gm you can tell. After that we are telling that this is bounded input bounded output stable if gk is absolutely summable. So in case of the continuous time system, we are telling that whatever this term g, basically gt is coming in place of gk, that is absolutely integrable. Now we are just telling that that is absolutely summable. So that kind of replacement we have done, and basically at the same time I can tell like this. So this theorem talks about if and only if. It means that if you assume that gk is absolutely summable, then you get bounded input bounded output behavior, and if you will get bounded input bounded output behavior, then equally I can talk about the impulse response sequence is absolutely summable, and proof is exactly same as continuous case. Again we will take absolute value because I have single input single output system. So this quantity just generate some kind of quantity which belongs to again real number. So due to that reason I can take the absolute value. And if you take the absolute value, so here inside summation, if absolute value will operate, then that absolute value of gm plus absolute value of uk minus m, and uk minus m is bounded, so output is bounded provided this summation term m equal to 0 to k, gm is bounded. So same way I can do proof. Due to that reason I am not going to prove it. Now let us try to see one example. So I have taken a very simple example, and we are going to check that this particular discrete time linear time invariant system is bounded input bounded output stable or not. So I am assuming here that impulse response is provided to us. If that is not provided, then you know that how to calculate. You can apply the impulse and try to calculate their value. And here this information is available at k equal to 1, 2 for any large value, and I am assuming that g equal to 0, that is 0. Now, in order to prove bounded input bounded output stability of discrete time system, what we have to do? We have to check the absolute summation of this impulse function sequence. So I have gk. So what I am going to prove now, that I am going to take the absolute value of this, and after that I am going to perform summation from k equal to 1 to infinity, and after that we will get this. Now I have to show that whatever value, that is s, if that is bounded input bounded output stable, then that will not going to converge towards infinity or minus infinity or plus infinity. But let us try to see that how to add this. You can see here that first term is 1, and after that this term 1 by 2. Obviously we know that how to calculate the summation. Another way, very easy way, you can just do grouping. So if you do grouping of 1 by 3, 1 by 4, so again I can tell that I have quantity 1 by 4 and another quantity, that is 1 by 3. So again 1 by 3 is larger than 1 by 4. So I am going to replace this by 1 by 4. So quantity is basically 1 by 4 or larger. So summation, due to that reason, we are telling that larger than half. Similarly, I will group here, and again I will come up to 1 by 2. So in this way I can tell that finally this will converge to infinity. So what you have observed, that in this particular sequence, what happens, that each instant you can see that this sequence is going to decay, and at infinity that is going to become 0. But what happens here? S is tending towards infinity. So we are telling that this impulse response sequence is bounded, because each time you can see that finally at very large k I will get some quantity that is very small. So this is bounded and approaches 0 as k equal to infinity, but it is not absolutely summable. So since this is not absolutely summable, so we have concluded that this is not bounded input bounded output stable. So if I have some kind of impulse response sequence that is given by 1 by k, then I can conclude that system is bounded input bounded output stable. And you can see that just by seeing impulse sequence I cannot tell anything, because here if you see the impulse sequence, then you feel like this, that okay, impulse sequence is going to decay in each and every instant, but finally what happens? But their absolute summation is not going to decay. Due to that reason, system is not bounded input bounded output stable. Now I have already told you that if I know that some linear time invariant system is bounded input bounded output stable, then I can give guarantee that if we will apply some bounded input or some class of input, then what is output? So I can quickly able to talk about the steady state response. A steady state response in case of continuous time system, we are putting t tending towards infinity. In case of discrete time system, we are putting k equal to infinity, because most of time we are concerned with the steady state. A steady state means, suppose I have a start our system, after some time what is behavior of my system. So due to that reason, most of time during circuit theory you might have observed that a large portion of course is just doing the analysis of a steady state. So if system is bounded input bounded output stable, same like continuous time LTI system, in case of discrete also we are getting the same kind of behavior. It means that if I apply some kind of UK, that is constant step response, then finally, as k tending towards infinity means in a steady state, value is going to approach to g cap 1 multiplied by a, where a is the step, whatever step signal I am going to give to the system. And what is g cap? G cap is the z transform of this impulse response sequence. So in case of, if you remember the previous lecture, at that time this is Laplace transform. Here in discrete time case, that is Laplace transform is just replaced by the Z transform and everything remains the same. Here in case of Laplace transform we are putting 0, here we are putting 1 because finally Gm is going to comes into picture. Now similarly I can tell that if I apply some kind of sinusoidal sequence to the system, then again response is going to converge to this. So quickly I am able to calculate what is the steady state response. There is no need to wait for the k equal to infinity. Just I have to make sure that my system is bounded input, bounded output stable, and these kind of analysis is pretty useful in case of digital signal processing. And proof is same like in previous class. I have told you that gm if uk minus m, that is a, so I can write like this, and after that if k tending towards infinity, then this summation is tending towards infinity, and finally I can generate this by putting z equal to 1. So in this way I can give guarantee that if system, discrete time system, is bounded input bounded output stable, and if I apply some kind of a step response, then what is my the final response. Now let us see the second proof, and again second proof is also again similar, exactly similar, just you have to replace now everything means integral by summation and gt continuous time signal by some kind of sequence. So I think that there is no need to means again discuss the same proof. Just for curiosity, what you can do, you can simplify this and after that put k equal to infinity, because I am just talking about the steady state response, means after very large time what is the response, large sequence what is the response in case of discrete time system. And since you know that this particular system is bounded input bounded output stable, and gk, it means that gk is absolutely summable, and so in place of z I am going to replace by e power j omega. So same like means that is the means same like e power in case of continuous time system I am replacing s by j omega, here z by e power j omega. So that is the relation, and after that if you simplify this, so again we will come up to this result. So what we have observed, that if you apply sinusoidal signal to a stable bounded input bounded output stable linear time discrete time linear invariant system, then frequency remains the same, just I have a scaling of the gain and after that the some shifting of the angle. So this is same proof like continuous case. Now one another way, by seeing the transfer function in case of single input single output system, it is pretty easy, same like continuous time system, I am able to talk about the stability. And here, because whenever we are seeing the transfer function means Laplace transform of the output by Laplace transform of the input. In case of discrete time system, we are telling that Z transform of output by Z transform of input when all initial condition equal to 0. So you can calculate that transfer function, and after that you can just check the pole of the polynomial, and if that is less than 1, then or at the same time we are telling that in z plane, if j cap z has a magnitude less than 1, it means that we are inside one unit circle. So if we are inside unit circle, then my single input single output system is bounded input bounded output stable. And proof is very simple, because you can see that suppose my transfer function has some pole and their multiplicity is mi. So again, what is role of Laplace transform or Z transform? They are transforming from time domain to frequency domain. And how basically one can move from frequency domain to time domain? By taking inverse transform, means inverse Laplace transform in case of continuous time system. In discrete time system, we have to calculate the inverse Z transform. I hope that during your first or second year of mathematics, you have already well aware about the Laplace transform, Z transform. If you are not aware, then please just go through any mathematics book. That is very simple, and several lectures are available on this domain. So suppose if pole has multiplicity mi, then again this kind of term up to mi comes into picture, and if you take the inverse of this, then this kind of term comes into picture. So pi power k comes into picture, and what you have to show that this should be absolutely integrable, and in order to do that, you have to make sure that pi value that should be not greater than 1. If that is greater than 1, then you are not able to prove that is absolutely summable. So in this way, we are, whenever we have discrete time system, by seeing the transfer function, one can talk about the stability. So far I have discussed about the input output stability of linear time system, continuous linear time system in previous class. In today's lecture, I have discussed about the discrete time extension of the same idea, and here absolute integrability is replaced by absolute summation. Now in next part of this lecture, I am going to talk about the bounded input bounded output stability or input output stability of time varying system. Before that, because whenever we are talking about this lecture and whenever we are going to multi input multi output case, so several time idea of norms comes into picture. Due to that reason, let us try to revise the norm. So I am not going to give the extensive discussion on this. You are able to find this lecture is also available on my YouTube channel. So if you want to go to detailed discussion, then please try to see the lecture, and this kind of concept is already available in several mathematics books. So basically, idea is that if I have just one dimensional quantity, then I can talk about the absolute value. And what basically absolute value is telling, suppose that you have certain quantity and you are here. So meaning of absolute value is that the distance, somehow some kind of distance from the origin we are telling. Now suppose if you are in two dimensional space, so and if you are here, so one can tell that distance from origin may be like this, distance one can calculate like this. So there are several many ways to talk about the distance. Similarly, if you are in higher dimensional space, then you are again different way to talk about the distance, and you have already seen that if I am in two dimensional space x and y, so from the school onward, you might have learned about this d square is x square plus y square. Similarly, if I am in three-dimensional space, so this concept can be extended like this. And similarly, I can tell that if that belongs to Rn, then x square plus y square plus z square and whatever Rn quantity, so summation will go like this. So now notion of distance is very important. And why that is very important? Because somehow by notion of distance we are able to compare some quantity. So in two-dimensional, if I do not know the notion of distance, so I cannot tell that this quantity and this quantity which is larger, because suppose you have to denote this quantity. How basically we are denoting? I am denoting with x-axis and y-axis, and suppose this is 5, 6. So I cannot tell that which particular vector is larger. So I cannot compare. So for comparison, we are introduced the notion of distance, and due to that reason, notion of distance is very important. Now let us see the generalization of this. So what we are telling, that suppose if you are in higher dimensional space and we have certain kind of limitation, we are assuming that that space satisfies certain kind of property, algebraic property, means that satisfy the linear summation and scalar multiplication people are telling, and that is called if that can, and after that 8 property they have to satisfy, and if 8 plus 2 means 10 property they have to satisfy. If they will satisfy, then that space is called vector space, and detailed lecture is available online, I have already told you. So I am assuming that whatever vectors I have taken here, that will satisfy the property of a scalar multiplication and vector addition with respect to certain property. And if you check any column vector, if every entry is real or complex, that will satisfy this property, and that is called linear vector space. And since I am in higher dimensional space, so I cannot compare two quantity. Due to that reason, I need the notion of distance. So I am mapping from this x is basically now some kind of space Rn, and this operator is called norm. So that is going to operate on this vector space, and after that they are going to create some kind of positive quantity. So this is some kind of real valued function, and if I have some kind of real valued one dimensional function, then one can compare it. So somehow due to that reason, we are telling that this quantity is the length of the vector. Now you might have seen that most of time I am writing x belongs to Rn or something like this. So what is meaning of this? This are telling that x has n number of component. So this is column vector, n number of component, and each entry is some kind of real number. Now I have already told you that there are several ways to define the distance. So one of way is like this. You can see the each entry and try to pick up the maximum one, and that is also one notion of the distance, and that norm is called L infinity norm. So I am going to see each entry and going to pick up just maximum one. And what is minimum? What is meaning of L1 norm? If I will take the absolute value of each quantity, and if I take the summation, that then that is called L1 norm. More detail why this kind of formulation comes into picture, I will teach you in the next semester. And for those who are interested now, please go through the lecture. And two norm I can define like this. Similarly, I can define the p norm. So this is a story if I have certain kind of column vector. So in column vector, you can see that I have different notions. So I can define distance using L infinity, L1, L2, and LP. And it is possible to show that any two, because several different definition of norm. And similarly, you can think like this. Whenever we are talking about the distance, so I can talk in meter, kilometer, centimeter, decimeter, all are somehow related. Similar kind of things is here. So two norm in finite dimensional space means n is not infinity. Somehow they are related, and that is called equivalent norm. So you can take any two norm, always this kind of relation comes into picture. Here some constant k1 and k2, that is going to comes into picture. So two norm, you can take any two norm, L1, L2, L infinity norm, and always you are going to see this relation. And I have already told you that this relation is only true in finite dimensional space, and if you have some kind of column vector and each entry is real number, so it is possible to show that infinity norm is somehow related to one norm by this relation, where n is number here n. So similarly for two norms, similarly for one norm, and this proof is a standard proof is available on the any textbook of mathematics. Now let us try to see that in place of Rn, now I am going to replace that by some kind of matrix Rn cross n matrix. So now I am telling that initially my space only contain the column vectors. Now suppose my space is going to contain some kind of matrix and each entry of matrix is some kind of real number, then that space is called linear matrix space or linear vector space, provided if we are talking about the addition and multiplication component wise. So I am assuming addition and multiplication component wise, then again they are forming some kind of vector space, and again if you have to denote some point p here, then this kind of matrix I can able to denote the point where this is called the basis. So basis in the matrix space, I have these kind of basis. So using that I can able to represent any point in the space. So either using column you can able to represent some point, using matrix you are also able to represent the same point. And now I am assuming that again that is vector space, so I can define some kind of notion of the distance that is called norm, and some linear space or linear vector space with norm is called non-linear space. So slowly you become comfortable with the terminology, and later part of the another course you are able to become more familiar with these kind of concept. So I have certain matrix n cross n matrix, so I can represent a11, a12, a1n, and similarly up to an1, and each entry is some kind of real number. Now I can define different norm. So I will see column wise, and after that the row wise. So what I am going to denote each and every element by aij, and if I keep I and varying j from 1 to n, then I am able to generate AI1, AI2 like that, and similarly 1 to M, because I am assuming that this is M cross N matrix. Then one notion of norm, again this is a scalar quantity. You can see that each time I am just talking about one element. And similarly this norm is called Frobenius norm, and in order to generate this norm, each quantity I will taking the square, and again I will add all row and column like this. And this norm is called AB. So here what we are telling, I am going to see each and every element and whatever maximum element that I am going to pick. So in this way I can define again notion of distance if I have some kind of matrix. And if I have told you that if I have certain point in a space, so I can represent that point using column vector. And how basically we are representing, suppose I have to represent this point x and y, so I can represent like this also, or you can put these two quantity here, so this forms some kind of matrix, and after that you can represent. So what we are telling that this point can be represented by some kind of column vector, and column vector is xy, and same point can be represented by a into xy, and where a is 1 0 and 0 1. So similar kind of, it means that what happens that I have some mapping between column space, means where each and every vector has a column, to matrix space, and this equivalence is again, using this equivalence one can generate the notion of norm, and that norm is called induced norm. And I have already told you that means if I have certain kind of matrix, then there exists some kind of correspondence in Rn space. So somehow that will map each matrix A belongs to Rn cross n. There is a corresponding linear map alpha from Rn to itself, and one can see similarly for third dimensional space one can see, and this particular observation gives another notion of norm, and that is called induced norm. And most of time in this literature, in this lecture, we are going to use this kind of norm, induced norm. So I am not going to the detailed definition of induced norm. Again I will come back to the lecture, and after that if you have means interest, then please try to see this lecture. And now let us come to the next part of this lecture. So here you can see that what I am telling, with help of, because we have already observed that there exists certain kind of relation between column vector and means a space filled by column vector, and same space I can represent using matrix. There exists correspondence, and due to that reason, with help of the norm in column space, I can define the norm in the matrix space. And in order to do that, I am going to project this. So what happens, that I am going to see the column vector, and after that I will take the norm and putting a norm equal to 1, and after that we are seeing the scaling. So somehow you can see that you can also interpret this as a some system. So you have x as a input, a is the some kind of transfer function matrix, and after that you are getting ax. So something like some scaling, some gain. And here supremum, I have already told you that if maximum will not define, then we are defining the supremum. Now, since what we have observed just now, that if I have column vector, so different way I can generate the norm. Due to that reason, matrix norm means induced norm of matrix is also not unique. If I select x1 as a 2 norm, then whatever norm, this norm is different. If I will choose infinity norm, then this norm become different. But obviously all are connected, because we have already seen that in finite dimensional space all norms are related. So let us see how basically people have defined the means a1 norm in one norm in case of the some kind of matrix. So here what we have to see, you have to check the each entry, and largest column absolute sum you have to select. So I have some kind of matrix, and after that I have to sum all the columns, and after that whatever largest sum of column, that largest number I will tell that is the norm of or a scaling of this particular x equal to 1, because here I am defining one norm. So here I am going to take column means norm of column vector using one norm. And how to calculate one norm? By taking the absolute value. And suppose you can take the two-dimensional space. So in two-dimensional space I have two vector x1 and x1 and x2. So if you calculate the norm of that, then means column norm of that or one norm of that, then that is absolute value x1 plus absolute value of x1, and that equal to 1, because we have to project with respect to 1, and this kind of shape comes into picture, because mod x1 plus mod x2 equal to 1, then this kind of shape comes into picture. So dark kind of shape comes into picture. And a, when you operate a, so some scaling happens, and basically whatever scaling, maximum scaling of some point from here to here, that I define. So geometrical picture of norm one can understand using this particular figure. Similarly, now you can see that two norm. So in case of two norm, and suppose you are in two-dimensional space, so you have to put keep column norm as a 2, so that is x1 square plus x2 square, and that is circle. And again if you apply a, then some deformation comes into picture. So whatever radial deformation, magnitude of radial deformation, that will give you a 2 norm. So largest signal means singular value of a, or largest eigenvalue of a transpose a, this represents the transpose. In this way you are able to calculate the a2 norm, and this is the geometrical picture. Similarly, infinity norm, how basically we are calculating infinity norm? We are taking maximum of xi. Here xi is x1 and x2, so it is possible to show that is nothing but this particular magnitude. So largest row absolute sum. So in place of a1 norm we are calculating largest column sum, here we are just replacing largest row sum. So using help of these three induced norm, now I am going to talk about the next part of this lecture, that is bounded input, bounded stability of the time varying system. And before going to do this, please see one exercise. So I have calculated I have taken 2 cross 2 matrix, and I have defined a1 norm, a2 norm, a3 a infinity norm. Please just check it. Now we all know that this kind of relation will exist. So again, it is very easy to prove. So sometime we are using this kind of relation. Now let us come to the bounded input bounded output stability of linear time varying system. So again, I am assuming system is on rest. I will apply some kind of input, and after that we are going to observe the output. And we have seen that, so the solution in case of time varying system, single input single output system, so that can be given again like this. And if that is bounded input bounded output stable, so for all t and t0, again initial condition now comes into picture, this should be bounded. And if that is bounded, then we are telling that linear time varying system is bounded input bounded output stable. So you have to means here integration from t0 to t, so you have to give guarantee that for all t there exists some kind of maximum value m. And similarly in multi input multi output case, now this impulse response is now converted into some kind of matrix. And now if you are going to talk about the boundedness, so in place of absolute value, because now y do not belongs to r, so y is some kind of matrix, so I have to use the matrix norm and or induced norm. We have just learned what is meaning of induced norm, and after that we have to see, and we have to see that again if you calculate the induced norm, some number comes into picture. So for all t, if this kind of relation will satisfy, then we are telling that multi-variable system, multi-variable or multi-input multi-output LTV system, linear time varying system, is bounded input bounded output stable. And in another way, how basically one can check the condition, because g t tau is now matrix, so you have to see the each and every entry, and if that is bounded, then we are telling that system means multi input multi output time varying system is bounded input bounded output stable. And I have already told you that in finite dimensional space all norms are equivalent, so you can take any norm, but most of time people are using infinity norm, so they are seeing the maximum of ui, and g infinity is the largest row absolute sum. Because you can see here that suppose if I am assuming that single input multi output system, then single input or the multi input multi output system, so this ut belongs to rp, so some kind of I have column vector. So in case of column vector I can define a norm like this, but in case of multi input multi output system, j is some kind of matrix, so we have to define some kind of induced norm. And how to define induced norm? By taking help of this infinity norm, and due to that reason we are telling that g infinity is largest row absolute sum, and this kind of norm people are using to prove the bounded input bounded output stability of time varying system. Now let us try to see the zero state response, because I am telling that all initial condition equal to 0, and at that time I can write the output like this, because we have already derived the solution in case of time varying system. And again if you have to show the stability, so you have to show that dt is also bounded, and after that this again this will the matrix norm, and that should be absolute, because somehow this will give you some number. So you have to show the whole integral is bounded by m2. So in this way, using the concept of induced norm, we are showing the stability of multi-input multi-output time varying system. Same can, whenever multi-input multi-output system involve, each and every time you have to go through the notion of induced norm, and due to that reason means you have to understand how to calculate the induced norm of some matrix. So now let us come to conclusion of this lecture. So what we have learned so far, that in last two classes I have talked about the one kind of stability for linear system, and that is called input to output stability, and that is somehow external stability. In next class I am going to talk about the internal stability. So at that time we are going to see that how basically external stability means input output stability is different from the internal stability. So with this remark I am going to close the today's lecture. Thank you very much.